code that allow to do that.
By Gernot Eichmann.
Okay, you can see it?
No problem.
Very good. Okay, so first of all, thanks to the organizers. I want to talk about exotic mesons with functional methods. And the first question here is, what exactly do we mean by exotic mesons? For heavy quarks, like here in the germanium spectrum, exotics are easier to identify because we have the quark model as a reference point to distinguish conventional from exotic mesons, simply by looking at deviations from the quark model expectations, as we just heard. Also, the large quark masses act as a filter, because if some unexpected state shows up in the germanium mass range, then presumably it has CC bar in it. And if it also carries charge like the Z states, then it cannot just be made of CC bar alone. So there are a couple of X, Y, and Z states here. The most prominent one is the X3872, which was first seen by Bell almost 20 years ago. It is extremely narrow and close to DD star threshold, so which points towards a molecular nature. And similar states have been found since then, like the X3915 and again the C states. And the large progress in this field is visible from a number of reviews that have been written just in the last couple of years. Now, if we go to light mesons, the situation becomes a lot more dilute, because here chiral symmetry and relativity start to become important, and the quark model is no longer fully reliable, so we need quantum field theory. A natural indication for exotic states is if they carry manifestly exotic quantum numbers like 1-, which cannot be easily created by QQ bar. And there are two candidates here, like the pi 1400 and pi 1600. They could be hybrids, or maybe there's really just one state here. But for other candidates, we can only infer their exotic nature from arguments like the overpopulation of multiplets or the unconventional properties, like, for example, the glue ball candidates, such as the F0 1700 or F0 1710 or F0 1500, or 4-quark candidates like the light scalar mesons. Here is the current experimental status. These are the established states up to 2 GeV for the various quantum numbers. I drew blobs around each presumptive multiplet so that things are easier to see. Inside each blob, we expect to find 9 states, 3 with isospin 1 in dark blue, 2 with isospin 0 in light blue, and the 4 kaons in green. For ideal mixing, we would expect to find a similar pattern as in the vector meson channel, where the omega is made of light quarks and almost mass degenerate with the rho meson, and the phi is the SS bar state. Now, in non-relativistic quantum mechanics, we can combine quark and antiquark to form spin 0 and spin 1, and together with orbital angular momentum, this gives us the expected level ordering. Orbital angular momentum 0 gives us the pseudoscalars and vectors, followed by orbital angular momentum 1, which gives us the 1+- and the 0, 1, 2++ states. And this is also how I arranged them here horizontally. Now, the obvious outliers are the 1- states, because they cannot be made in this way. But if you combine a quark, an antiquark, and a gluon, then this is a natural quantum number to expect. So these may be hybrids. An overpopulation of multiplets starts to set in above 1.4 GeV, where things get messier. For example, either the F0 1710 or the F0 1500 may be a glue ball. And there are other candidates like the Ada 1405, although it's not clear if these are really 2 different states. And the lonely guys up there could be the onset of new multiplets. The other outliers are the light scalar mesons, because here nothing works. The mass ordering inside the multiplet doesn't work out, because instead of the A0 being mass degenerate with the sigma, it is almost degenerate with the F0, which doesn't make any sense. And also the mass ordering between the multiplets that we would expect, the mass ordering between the quantum numbers that we would expect from here, would also only work if we ignored the light scalar mesons entirely. So just to refresh your memory on the sigma meson or F0 500, it appears as a resonance in pi-pi scattering. But in contrast to the rho meson, which has a clear bump, the sigma only appears as a broad shoulder. So for a long time, it was not clear whether it's really there or not. By 2010, it was in the PDG again under the name F0 600, with a mass range between 400 and 1200 MeV. This is the large blue rectangle here in the complex plane of square root of S. But since then, this has been pinned down quite precisely by dispersive analysis, which is the small red rectangle here. And as a result, the PDG now was the slightly larger red rectangle and the mass range of 400 to 550 MeV. And they also renamed it to F0 500. And also lattice QCD has made substantial progress in determining the phase shifts from pi-pi scattering and pinning down the pole position in the complex plane. So this tells us that the sigma appears as a pole in pi-pi scattering, but what is its internal structure? If I zoom into the multiplet, then again, if these were QQ bar states, then the A naught and sigma would be the lightest states, followed by the kappa with one strange quark and the F naught with two strange quarks. But this doesn't work out because the A naught has almost the same mass as the F naught. Also, the decay widths are very different. The sigma and kappa are broad states, whereas the A naught and F naught are relatively narrow. So the idea going back to Chaffee was, what if they were tetraquarks in the sense of diquark anti-diquark? If you combine a scalar diquark with a scalar anti-diquark, you still get a nonad of states, but now the mass ordering is reversed. The sigma is the lightest state, followed by the kappa with one strange quark, and the A naught and F naught with two strange quarks. So this would immediately explain the mass ordering. It also explains the decay widths. The A naught and F naught are close or just below kk bar threshold, so they do not decay, whereas the sigma is above pi threshold and the kappa above k pi threshold. So they can simply fall apart into two mesons without exchanging gluons, which would make them broad. An alternative would be meson molecules. The sigma appears in pi and the kappa in k pi, so they could be dynamically generated resonances. The A naught and F naught sit at kk bar threshold, so they could be kk bar molecules. And there's been quite some history of support for the non-QQ bar nature of the light scalar mesons from various approaches. So what can we say about that? Here's the one-slide summary on functional methods in order to calculate bound states or resonances of n quarks or antiquarks in QCD. We solve covariant bound state equations. They go by different names, beta sub beta, Faddeev-Jakubowski equations. A simple way to think about them is as the quantum field theoretical analog of the Schrödinger equation. The Schrödinger equation gives you the energy and the wave function of the system. From here you get the mass of the hadron and the wave function, which is the beta sub beta amplitude. So with this, we can do spectroscopy calculations. To solve these equations, we need to know what goes into the kernel, and these are QCD's endpoint functions or green functions or Schwinger functions. For example, the dressed quark propagator is what becomes of a quark if we switch on quantum loop effects, which are described by the Dyson-Schwinger equations, which are QCD's quantum equations of motion. One outcome of this is the dynamical generation of a quark mass, which interpolates between the current quark mass at large momenta and a constituent-like mass at low momenta due to dynamical chiral breaking. But we also need to know the gluon propagator and higher endpoint functions, like the quark gluon vertex, the 3-gluon vertex, and so on. Their equations back couple into the ones you see here. So in the end, this becomes an infinitely coupled system. And then the idea is to start with the lowest endpoint functions, let's say the 2-point, 3-point functions, ideally also the 4-point functions, calculate them into good precision, compare with lattice QCD, and use this to compute hadronic observables. Once we know the wave functions, we can do hadronic structure calculations, for example, for form factors, PDFs, two-photon processes, and so on. There's been a body of work using the rainbow ladder truncation, where the two-body kernels that go into these equations are taken to be a gluon exchange with some momentum-dependent dressing function. This is a model that has been often used. At large momenta, it is constrained by perturbative QCD. At low momenta, it depends on a shape parameter, which controls the bands that you see here. This is the rho meson mass, the nucleon mass, the delta mass, as a function of the squared pion mass and compared to lattice QCD. But that's it. There are no further approximations. So once you've settled on this, you can take it away and compute meson and baryon spectra, elastic and transition form factors, and more. And much of this is collected in our review article from a couple of years ago. And recently, the three-body equation has also been solved for heavy baryons. In practice, what we do is we keep the full structure of the beta sub beta and Faddeev amplitudes. If you take all the traces, then this boils down to an eigenvalue equation for a large kernel matrix. For a three-body system, the dimension of the matrix is typically of the size of a million by million up to a billion by billion. An interesting question concerns diquark correlations. One can simplify the three-body equation to a quark-diquark two-body equation, which amounts to a ping-pong exchange of a quark between the other quarks. And also here, one can calculate everything from the same interaction without further approximations. And in that way, one can directly compare the 3-quark and quark-diquark results. This is the nucleon excitation spectrum. The red boxes are PDG. The blue boxes are the 3-body and the quark-diquark results. And they compare quite well, where such a comparison is possible, like for the nucleon, the Roper resonance, the delta resonance. And they also compare well with the experiment. And similar things happen for form factors, etc. So this points towards a diquark clustering in baryons. Now, to take this further, we have to go beyond rainbow ladder and also compute higher endpoint functions like the 3-gluon vertex, the quark-gluon vertex, etc. And there's been quite some progress in recent years to a point where precision studies have come within reach. So here I compared the Dyson-Schwinger versus lattice results for the gluon propagator, and as a result of long years of numerical improvements, they are nicely in agreement. So here there are no model parameters anymore. The only approximations are to neglect higher endpoint functions. There's been quite a fruitful interplay between Dyson-Schwinger equations, the functional renormalization group, and lattice calculations, to a point where ab initio calculations for hadrons are coming within reach. And this improves things a lot. So for example, here you see the light meson spectrum for different quantum numbers. The red boxes are PDG, the gray boxes are rainbow ladder results, and the blue boxes are beyond rainbow ladder. So in this case, rainbow ladder really only works for the pion and the rho meson, which you cannot see because everything is on top of each other. But for the other channels and the excited states, they come out too low. But if we go beyond rainbow ladder, then they are pushed up into the right ballpark. This means we are on the right track. To get reliable results, we need to include higher endpoint functions. By the way, the 3 channels here on the right are exotic quantum numbers. This is the 1- channel, but this comes from a quark-antiquark BSE, which is, however, relativistic. So once the kernel becomes rich in gluons, then also these exotic states are pushed up and start to appear making sense. Another example are glue ball calculations in Young-Mills theory, which means QCD without quarks. Here one can derive coupled glue ball ghost ball equations from the quantum effective action, where the kernels are directly related to QCD's endpoint functions. So also here, there are no model parameters. The only approximations are to neglect higher endpoint functions. This is a recent calculation, and you see that it compares quite well with the lattice. So this is the scalar glue ball and its excitations, the pseudo-scalar glue ball. So according to this, the lowest lying scalar glue ball would appear somewhere in the 1.7 GeV range, at least in Young-Mills theory, without dynamical quarks. Another area of improvement is to include the resonance dynamics. This is quite non-trivial here because we are not working in an effective field theory where the intermediate hadrons can go on shell and automatically produce cuts and resonance poles. Instead, the kernels have to dynamically generate such poles, for example, pi in the case of a rho meson. But once these effects are included, the rho meson becomes a resonance and indeed develops a pole on the second Riemann sheet. And the numerical tools to accomplish this is to use contour deformations in the complex plane. Because once you have internal poles and more than one integration, they will produce branch cuts which interfere with the integration contour, which then has to be deformed. But in this way, we can solve the beta-beta equations on the whole complex plane. Here's an example for a scalar model. This is the first Riemann sheet. This is the second Riemann sheet. So one can track the pole trajectories here. And we are also applying this now to QCD. Now coming to 4-quark states, here we solved the 4-body equation for systems made of 2 quarks and 2 antiquarks. But in this case, things blow pretty much out of proportion because once you have 4 independent quark momenta, you can construct 9 Lorentz invariants from them on which the amplitudes depend and hundreds of Dirac tensors. Just to give you an idea, when you break this down to an eigenvalue equation, then the dimension of the kernel matrix for mesons is typically of the order 1000, which only needs 20 megabytes for storage. So that's no problem. But already for baryons, it goes to the million to billion range. So you would need 10 to the 7 gigabytes and more, which is no longer possible. So we have to trade memory for CPU time. And then for tetraquarks, this gets completely out of hand. So that's no longer possible to solve yet without approximations. And one needs to develop smarter algorithms to get this done. So what we did here is we grouped these momentum variables into multiplets of the permutation group S4, because in this way we can switch off bunches of variables without destroying the symmetries of the system. The S0 here is the symmetric variable. The triangle is two-dimensional, so this is a doublet which contains two variables. This is a tetrahedron which lives in 3 dimensions, so it's a triplet. And this is a ball, also in 3 dimensions. So we have 3 plus 3 plus 2 plus 1 is 9 variables. And then what happens is very interesting. If we switch off everything except for the symmetric variable, the tetraquark mass that comes out is about 1500 MeV, which is about 350 MeV times 4. So it's like 4 times the constituent quark mass, which is what you might expect if you put together 4 quarks. So adding any of these triplets doesn't change too much, but a huge effect comes if we switch on the doublet, because then the mass drops down to 350 MeV. So apparently the doublet contains the important momentum dependence. And the reason is that the 4-body equation dynamically develops meson poles, even though the equation doesn't know anything about mesons. It's just quarks and gluons. So that's what I meant before. The resonance mechanism in terms of internal meson poles, which then produce branch cuts and Riemann sheets, etc., should be generated dynamically from the quarks and gluons. And this is what happens here. Kinematically, the poles only appear in this triangle, so the resonance mechanism lives inside the triangle, so we can switch it on or off. The 3 sides of this triangle correspond to the possible 2-body clusters in the system: diquark, anti-diquark, meson, 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 meson. So it's like a Dalitz plot of the beta amplitude. So on the meson-meson sides, you can see the pion poles which emerge, which come close to the integration region because the pions are so light, so they dominate the system. And these are the results. The boxes are the PDG and the bands are our results around the light current quark mass. So we are qualitatively in the same region. And by the way, this also explains why the light scalar mesons are so light, because the problem with the diquark anti-diquark interpretation is that the typical diquark mass scales for a scalar diquark is 800 MeV. So if you put together 2 diquarks, then why would the resulting mass come down all the way to 400 MeV? But if the dominant 2-body clusters are not diquarks but mesons, then it's clear that the 4-quark states are dominated by the pseudoscalar Goldstone bosons, so they inherit their lightness from the light pions and kaons. This can be made even more explicit by going to a 2-body formulation. This is the analog of the quark-diquark formulation for baryons, which is derived from the 3-body equation. Here we start from the 4-body equation and end up with a meson-meson diquark anti-diquark system, which is coupled. So the meson-meson amplitude couples to itself and to the diquark anti-diquark amplitude, which couples back to the meson-meson amplitude. And you see the kernels here are not hadronic exchanges, which you would get in an effective field theory, but quark exchanges. So just by looking at these kernels, it is not obvious why a system that is dominated by meson-meson would be less compact than a diquark anti-diquark dominated system. In fact, the system wants to be meson-meson-like because there is no diagonal diquark anti-diquark term here, because you cannot exchange quarks between a diquark and an anti-diquark. So I cannot even switch off the meson-meson component because then there is nothing left of this equation. But I could switch off the diquark anti-diquark part. Then I still have the meson-meson equation. And also here we get similar results as in the 4-body approach. For example, the mass of the signal comes out at around 400 MeV. Another advantage of the 2-body formulation is that one can include a mixing with QQ bar, which becomes another row and column in this matrix. So this thing here would be the QQ bar system alone, but now it is back coupled to the meson-meson diquark anti-diquark system. And what happens is that pi is still dominant. Pi alone would give a mass of about 420 MeV. Adding the diquarks doesn't change that. The QQ bar alone in rainbow letter comes out at around 670 MeV. And if it's back coupled, then it just changes the pi mass by a little bit. So it goes up to 450 MeV. So the original assumption was good. The light scalar mesons seem to be really dominated by meson-meson components. Whether this is still true for heavy light 4-quark candidates remains to be seen, but what we can say at this point is that the hidden charm states with CC bar also have a strong meson-meson component. So here, in this case, the 3 sides of the triangle would correspond to the 3 possible 2-body clusters, meson molecule made of two heavy light mesons, hydrogen with a heavy meson and a light meson, and a diquark anti-diquark configuration. And when we put these three together, then the meson molecule component still dominates. So for example, here in the X3872 channel, which is dominated by DD star, if we add the other components, then this doesn't change anything. So the hidden charm states have a strong meson-meson component, whereas for the open charm states, we see that diquarks also seem to play a role. Okay, now switching gears a bit, what about hybrids? In principle, one should solve a three-body equation made of quark, antiquark, and gluon. We are still working on this, so this is in progress. Recently, a two-body version of this has been studied by these authors from a quark-gluon antiquark two-body system, based on the argument that the interaction in the color triplet octet channel is attractive, as opposed to the quark-antiquark color octet channel. So this is similar in spirit to the quark-diquark approximation, except that here we have a ping-pong exchange of the gluon between the quark and the antiquark. And these are the results. So the green bars are the results, and the purple and blue bars are lattice results. So even though there are quite some approximations here, because many of these quantities are still unknown, it looks like there could be a number of hybrid candidates in the 1.6 to 2 GeV region. Okay, now to finish this off, what about pentaquarks? The LHCb pentaquarks sit close to meson-baryon threshold, so they look like meson-baryon molecules. So the simplest thing to do would be to solve a meson-baryon two-body beta-sub-beta equation with hadronic exchanges. This is what my master student did, Madalena Lorenzo. She solved a coupled channel BSE, including sigma CD star, proton eta C, proton J psi, and with the lowest lying hadronic exchanges in each channel. Now there are a couple of unknown couplings here, so there's not really a lot of predictivity, but we wanted to see how the system reacts, especially when we solve it as a genuine four-dimensional integral equation. There has been some work on that by Tobias, Federico, and Gianni Salme and collaborators. They calculated the ground states for generic fermion scalar and fermion vector systems using the Nakanishi representation. And they found some inherent problems in binding the system. Here we calculated also the higher lying eigenvalues. And what we find is that eventually the eigenvalues start to cross and produce complex conjugate eigenvalues. So what looks like a kink here is not really a kink, but it's the crossing of different eigenvalues. So if you continue this plot, to higher excitations, it would eventually start to look like a spider web. This is a typical feature of unequal mass systems, and it has to do with the so-called anomalous states that are features or artifacts of four-dimensional integral equations. It's not really clear yet where they come from, but the possibility is that they're simply artifacts of too severe truncations. In any case, there's a simple way to get rid of them using a spectral reconstruction. So if we solve the system but keep only the positive eigenvalues of the propagator matrix, then all these things go away. So we can disentangle the structure and we get nice and clear eigenvalues. So here we can infer what the dominant structures are for each eigenvalue. So for example, this one would be sigma CD, and this one also, and the dark blue one would be sigma CD star, and then these are the resulting masses. Okay, so the road ahead for functional methods on exotic mesons is summarized here. So we recently wrote a short review on our work on 4-quark states. There is movement towards ab initio calculations, which means to include higher endpoint functions and resonance properties. Hybrid mesons are underway. And next on the list are exotic baryons, like pentaquarks and dibaryons, which could also lead to interesting effects in the light quark sector. So with that, I conclude. Thank you.
Thank you for the very nice talk. Questions? Adam, please.
Yes. Hi, Gernot. Very nice talk.
Hi.
So the hybrid spectrum, I remember in the past hybrids were supposed to be just quark antiquarks in this formalism, but now you say it's solving three-body equations. So
well, the strategy is twofold, right? So on the one hand, quark antiquark, on the other hand, also three-body equations, right? So ideally, I mean, the point of view is that ideally it shouldn't matter, right? So if you put full QCD in this kernel or in a quark-antiquark kernel, you should presumably get the same spectrum, which includes everything, including hybrids.
Not coupled anymore, or is
no, everything is coupled. I mean, there's a simple argument, right? But I can go back to my backup section. Right, so QCD tells us that any correlation function which allows for particular quantum numbers will have the same spectrum, right? So if I look in a quark-antiquark correlation function,
I understand that, but
right?
I'm asking this calculation that you were referring to towards the end. These two wave functions are not coupled: the quark-antiquark and quark-antiquark gluon.
So these are no, but I mean it just depends on the complexity of the kernel, right? So for example, if I go back to the quark-antiquark calculation, where was it? Here. So this is a quark-antiquark calculation, right? But once you start to fill up your kernel with gluons, naively speaking, you get these effects that are important to describe hybrids. So at least that is what it looks like, right? So ideally, if you have the full quark-antiquark kernel in QCD, ideally, right? So I'm just saying.
I just wonder why if in the past you guys solved the quark-antiquark for the hybrids and now it's quark-antiquark.
No, we're doing both. Well, I mean, the quark-antiquark will of course work better for states that are dominated by quark-antiquark, right? If you start directly from a three-body equation, quark-antiquark gluon, this will work better for states which are dominated by hybrids, right? So if you want to study hybrids, it's probably better to start from a three-body equation because you might easier see the
but you're getting the same 1 minus plus quantum numbers from quark-antiquark, aren't you?
Eventually you should get the same, yes. It just depends on the truncation. So with better and better truncations, the hope is eventually you should get the same.
Okay, Victor, please.
Would it be possible to compute spectrum, photo and electrocoupling of hybrid baryon, free-dressed quark and one-dressed gluon?
Yes, why not? This would certainly be possible.
Experiment in 12 GeV era at Jefferson Laboratory focused on the search of hybrid baryon in electroproduction, and such computation would be extremely useful.
Right.
Thank you.
Right. As I said, I mean, this is still in progress, right? So first we need to get a spectrum, then we can talk about form factors, etc. But I mean, yes, that's certainly interesting and something you should do. Yes.
Okay, next question, Jorge, please.
Hi, Gernot.
Hi.
Very nice talk. When you compute the sigma mass, considering also the QQ bar configuration, you should couple both meson-meson, the quark-anti-quark, and QQ bar configurations. What is the kind of interaction that you have in order to couple them, all these three channels?
This is basically what you see on the slide, right? So if you have meson-meson, diquark, anti-diquark alone, then you would have quark exchanges. If you had only QQ bar, then you would have only this. So if they were not coupled, then these guys would be zero, right? So these are the coupling terms that you see here.
Okay.
So you break up, so you have meson-meson, and which produces intermediate QQ bar, and you have QQ bar, which produces intermediate for quark, which becomes meson-meson or diquark, anti-diquark.
Okay, and just related with the mass that you are getting there. So for QQ bar, I see that you have 700 MeV, and for the pi configuration, you have 400 MeV.
Right.
When you couple both configurations, you should have, in general, two poles, isn't it? You have one below and one up. What is this one, 472?
472, no. So if you couple everything, then you get just this. So these are your two poles. If you
okay,
right?
I see.
And furthermore, more excited states, of course, but these are the lowest lying poles.
Okay. Okay.
So basically the leading pole is still that of the pi-pi system. And interestingly, the first excited state basically looks like the first excited state that we got before. So it's the question, is this maybe QQ bar dominated, which would be in line with the idea that, you know, the first excited state in the sigma channel, in the scalar meson channel would be QQ bar dominated, and the lowest lying state is 4-quark dominated. So this seems to go in that direction.
Okay, thanks.
Sure, thanks.
So we have one more question from Lang Tian Liu, please.
Hi, Eichmann. Thank you for your very nice talk. And I want to ask, how do you deal with the complex eigenvalue?
Complex eigenvalue. Oh, yeah. Yeah, that's a good question. So that's maybe a longer question. So maybe we should shift this to the discussion session. So I don't know. The point is, well, I have a slide here. So the problem is that even in the simplest Wick-Kotkowski model for unequal masses, this is the eigenvalue spectrum you get. So you see real poles which turn into complex poles and so on. So this was also studied by Reinhardt and other people in the past. If you have complex eigenvalues, then this means that your system is not Hermitian, right? So what does this mean? So I had a look at this, and you can actually show that both the kernel and the propagator matrix are Hermitian, even for unequal mass states. So if they both are Hermitian, this can only mean that the product is not Hermitian, which means they do not commute. Of course, they do not commute, right? So this is an inherent feature of the equation, if you want. So I looked at, okay, what can happen so that the whole thing, why is the whole thing not Hermitian? And I found the Cholesky decomposition, which says that if you have a Hermitian matrix, which is also positive, you can write it like this, and you can turn the system into a Hermitian problem. So if this is my propagator matrix, and I know it's Hermitian, then the problem can only come from here. It's not positive. So I looked at it, and yes, indeed, it has positive and negative eigenvalues. So if I restrict it to positive or negative eigenvalues only, then I get a very interesting thing. So then I get this spectrum here. So the red one is only for positive eigenvalues, and the blue one is only for negative eigenvalues. And then you see exactly what you want to see. You see avoided level crossings, etc. So the red spectrum looks like the physical spectrum, and the blue spectrum looks like what we would call anomalous states. Those that do not go down, because they need to go down eventually to produce a pole. They need to cross the one. So this looks very interesting. And actually, you can do the same for the pion. So this is the pion excitation spectrum in QCD in rainbow ladder. So also here you have these effects. So if you disentangle them, you see a nice eigenvalue spectrum in red, and you see two anomalous states, if you want. And this works beautifully. So for the Pentaquark system, I mean, you wouldn't even see, you couldn't even distinguish the eigenvalues because it just looks crazy. But if you apply this, then everything is gone. So it looks perfect. So I think
You project the positive eigenvalue.
right. So this would be the positive eigenvalues, yes.
Okay.
So it looks to me like this thing is a truncation artifact. So the more severe your truncation is, the more and more these things start to happen. But it could be some other explanation as well.
Okay, I see. Thank you.
Okay, thank you.